All right, well, I might get started. So first, welcome to everybody to the first signature lecture of the year for the ARC Center of Excellence for Enabling Eco-Efficient Beneficiation of Minerals. I'd like to start by acknowledging the traditional custodians of country throughout Australia and their connection to land, sea, and community. We pay our respects to their elders, past, present, and emerging, and extend that respect to all Aboriginal and Torres Strait Islander people today. Today, we're lucky enough to have Kathy Ehrig from BHP Olympic Dam as our signature lecturer. Kathy is one of those rare industry people who has a track record equivalent to a professor with more than 100 publications, 10 or 12, I forget, PhD students, supervision, ARC grants, and likewise. In addition, she has a mineral named after her, which is a bismuth telluride, which is a unique thing. And so Kathy's going to talk to us today about critical minerals and a little bit about career opportunities in the mineral processing sector. So thanks for that. And with that, I'll let Kathy take over.
Okay, and thank you, George, for the invite. And more importantly, thank you for doing the acknowledgement of the country, because we're all very astutely aware of that everywhere we have to operate, even around the world. Now, I have been in the mining industry for 33 years. And before that, when I was doing my PhD, I also worked for the US Navy, but not as a military person, as a civilian. And I was doing geothermal exploration and terminal ballistics. So kind of a real mixed bag background. And today's presentation is going to be about Olympic Dam, but talking about critical minerals, but more of the focus on with the different disciplines and the postdoc studies that people are doing now, that there is a need for all that work across in the mining industry, so I'll say the minerals industry is better. And so it's just an awareness that I have a very mixed background. I'm sure a lot of you do too, but there's opportunities and you're only limited by what you can imagine. Now, when I show things, I'm a geologist and I've worked around metallurgists for 33 years. And what I tell them, I've learned a lot about metallurgy, and I always tell my operating friends that I know enough metallurgy to be dangerous but not useful, and so if we keep that understanding at that level, it's pretty good. Now, in my presentations, I actually always show minerals, because everything we do when we take dirt out of the ground and we're going to extract a metal out of it, it's presented to the plants via a mineral. A mixed bag of minerals. And so we have to remember that. And these are just a few SEM shots. And looking at the scale bars in the lower right-hand corner of each one, there's some at 20 microns, 120. These are the size of things that we're going after. So the ones on the right-hand side is a hematite grain, and you see all those little tiny bright white specks in there, and that's uraninite. And we do produce uranium. And that uranium at that scale is just the tip of the iceberg. And as our microanalytical instrumentation capabilities have dramatically improved over time, we not only have to characterize stuff at the macroscopic scale, we even now go down to the nanoscale, and actually to try to understand how these systems are behaving, and then what's the impact on metallurgy. So that's just a little thing for uranium. The other two just show some rare earth minerals, and we're going to just talk about rare earth minerals a little bit, and just some of their occurrences. So at OD, they're very, very small, scattered all over the place. They're not these nice big things. I would dearly love to have our rare earth minerals being more than 20 microns in size, but most of them aren't. So we'll go to the next slide, George. And George, thanks, George, for being my button pusher. We're going to skip that disclaimer. You can get it from George if you'd like to read it. Now go on to the next one, George. BHP is the world's largest mining company. We employ about 80,000 people around the world. And they're really broken into three major groups with the operations: what's called Minerals Australia, which has iron, coal, and nickel. Recently created Copper South Australia, which is really focused on the copper deposits within South Australia that are near Olympic Dam, Carrapateena, Prominent Hill, and then one we have in the exploration phase. And then Minerals America, which is really around the porphyry copper deposits, and the Jansen project in Canada, the potash project. We've changed the time to be commodity based and then regional based and all that. And so this is just our latest maceration. Now, BHP also has a lot of other assets that they manage, are involved with. We have a lot of non-operating mines, joint ventures, and there's just a lot of other stuff. So get on their website if you really want to delve into it a lot more. Next slide. So I'm all about Olympic Dam, and this table here shows the world's largest base metal deposits, and these are the giants at the very top. And this work is from Richard Shoddy at Mindex Consulting, excellent source of information about the minerals industry and in exploration success. And what it does is most of these deposits are polymetallic, but it tries to relate it all to like a copper equivalent metal tons. And the biggest base metal deposit on the planet is Norilsk, frankly, out of Siberia. Nickel, copper, PGEs, really, and all kinds of other things. And then there's a bunch of other ones that are just a little bit behind that. And Olympic Dam's in there. Our positions can shift a little bit depending on what's going on with the resource, but we are big. Then there's hundreds of deposits that fall in underneath. So why have always been fascinated with Olympic Dam. We're going to talk a little bit more details about that, but it is one of the biggest ore deposits on this planet, and it just happens to sit in Australia. So that's fantastic. Next slide, George. Olympic Dam, we're going to zoom into it quickly. The little tiny orange dot on that map of Australia shows where Olympic Dam is, and the other deposits in our area sit very, very close to there. And we're about 550 kilometers northwest of Adelaide. And just hit a button one more time, George. I have some words there. And what this shows is just an oblique view of looking at Olympic Dam and the operation. So we see a lot of activity on the surface, but we're an underground mine, and the mine really sits really off in the background. And what we see from air, and we'll look at air photos a little bit later on, is all the ventilation shafts are associated with the mine, but you really see the whole processing plant. So we go from underground mining of a mechanized sub-level open stope mining. Then we have a grinding and sulfide concentrator. There's a hydrometallurgical circuit of which we produce uranium ore concentrate out of that. We have a direct-to-blister smelter, a sulfuric acid plant, and we have ER and EW copper refineries where we produce 5/9 pure copper cathode. We also have a precious metals refinery on site that recovers gold and silver, or produces gold and silver bullion. Now we have all these things here because Olympic Dam, we do produce uranium, and because we have uranium occurs across the entire deposit and all the minerals, we actually have to go through. And long ago, they actually had to build the whole facility on site. We cannot ship concentrates around the world. So the benefit of that is having everything there, and you can learn a massive amount about the whole business by just working at Olympic Dam, going from the mine all the way through the refined products. And I've had the privilege of being able to look at material all the way from drill core in the early days of discovery, all the way up until final products. And that's what I spend a lot of my time actually doing, is understanding the mineralogy and the behavior all the way of all these minerals from the beginning to the end of the process. Next slide, George. And this year we're recognizing the 50th year since the discovery of Olympic Dam. And about within a few days, the first drill hole into the unknown deposit was started back in mid-June 1975. And no, I didn't start in 75 at Olympic Dam. I started in 1992, but the deposit was discovered 50 years ago. The Olympic Dam deposit was discovered by the former Western Mining Corporation in July 1975 when they actually ended the hole, but it wasn't announced for a few years because they had to do all kinds of drill outs. It is, and there'll be minimum geological language here, it's a breccia-hosted iron oxide, copper, uranium, gold, silver deposit. And this what's now called an IOCG, was the first deposit type of its to be discovered. WMC was looking for a sediment-hosted copper deposit, and they found something different. The discovery story is well documented. It's regarded as one of the 20th century's best exploration success stories. So in a modern sense, we talk a lot about exploration undercover. You know, it's kind of been a common language for a long time. This deposit was discovered under 350 meters of rock that was unmineralized and 1 billion years younger than the deposit. So it was discovered 50 years undercover. The operations actually officially opened in 1988, and Olympic Dam is one of the largest mineable accumulations of copper, uranium, gold in the world. And our resource continues to grow. So here's just a picture of two of the externally published books about Olympic Dam. And the interesting thing after all this time, and it's still applicable back now, is the quote that was from our managing director of WMC, Sir R.V. Parbo. And his comment was, nobody knew how big it would be. And he made that comment back in the 90s. We are still adding dirt to these days, deeper and deeper in the deposit, but we're still adding resources on. Next slide, George. That's it. So since 1988, what have we actually done there? We've milled 255 million tons of ore. We've produced 5.2 million tons of copper cathode, 180,000 tons of UOC, 3 million ounces of gold, 24 million ounces of silver, but more importantly, we also have about 250 million tons of tailings. When people talk about, you know, you're throwing material away, no, we're not. It's sitting on the surface, and it's there as a resource for future generations to extract. So cool. Next one. In Copper South Australia, and our IOCG deposits, besides containing copper, uranium, gold, and silver, they also are host to many critical minerals. And this is what's unique about the IOCGs, is the real mixed bag of elements that they happen to have in them. So the green in the periodic table there, the green boxes are the metals that we produce. The red ones are the radionuclides that are associated with the decay of uranium that we actually have to be concerned about, even though it's relatively low, but that's why we have a process plant at Olympic Dam, is in order to deal with those. Now, those other elements that are kind of in that pale brownish color are other elements that are enriched in the deposit, and the speckled ones are other ones that are in the deposit too, not at super high levels, but nonetheless there. So as commodity prices change with time, we monitor all this material and actually are asking ourselves on a regular basis, what more can we get out of the ground, and what more, not only get out of the ground, what more can we process and make a sellable product? Because at the end of the day, it could be the best ore deposit in the world, but it has no value until it's converted by metallurgy, chemical engineers, to a sellable product. Next slide, George. So yeah, that's okay. Don't go anywhere. What I'm going to do is focus a little bit on the rare earths, because that's always very topical, and it's incredibly topical over the last 10 to 15 years, and it continues to be. There's not a shortage of rare earths in the world. It's a geopolitical problem, you know, and so we just have to remind ourselves of that. And so rare earths, this is another example from Richard Shoddy's Minex Consulting website. That we're on here, you can look at a map of the global distribution of rare earths deposits around the world, sized for what they were, sized according to what the size of the deposit is, and whether rare earths are a primary product or a potential byproduct out of there. And we can see the big, huge circles in China, and then the other ones around the world. And Olympic Dam is right next in size up to that. Next one. So everybody gets excited. So we're going to be in metallurgy land. Olympic Dam is the world's second largest metalliferous deposit on the planet. And because we have a very high tonnage, often relatively low grade material equates to a lot of in situ metal tons. But we know as from the processing side of the world that in situ tons doesn't necessarily equate to a recoverable product. And we have to remind ourselves sometimes that the world's oceans are the biggest resource of damn near the whole periodic table anyway, but we don't mind the ocean water, so we have to rescale our thinking. And when geologists talk about deposits, and particularly the ones that are exploring from them, they get incredibly excited when we have a little tiny bit of a concentration of a metal in an area that's slightly above crustal abundance area, but we don't mine crustal abundance. We actually have to mine higher grade deposits. And the rare earths is a classic example. So we don't have an official publicly declared resource for the rare earths at Olympic Dam because we don't produce them, but there is a rough idea about how much is there. And what this shows is the total rare earth oxide, and both axes are on a log scale, and then the grade of those deposits on the vertical scale, again on a log scale. Bionobo, which is without doubt the world's largest rare earth deposit, and there sits Olympic Dam. And you say, well, we're quite high. Kind of a magic line. If we put a rough line around it, and it changes a little bit, the deposits that are really in production are really above that 1% rare earths. And Olympic Dam sits below it, and there's a lot of other deposits of which most of them aren't being mined. And this discussion is not going to talk about these ionic clay deposits. They're really about more material that's sitting in it, because the ionic clay deposits are, the way they've been mined to date, are an environmental disaster. So in the West, nobody really touches those things. But you can see Olympic Dam is up there, and our size is up there, with Bionobo, not quite as high grade, but the tonnages are pretty close. But does that mean it's effective to do that, to recover it from Olympic Dam? Next slide, please. So we're just going to take a little digression, and we get all excited on the difference whether something's light rare earth or heavy rare earth enriched, and the perception that the heavy rare earths are worth more. Sure, they are, but what's the actual stream of these things? So a lot of things on the net, and a couple years ago I heard a presentation by Darren Smith, which was pretty good, and the YouTube link is there, and it shows that. And his comments down there, in the current and foreseeable market, rare earth deposits economics are fundamentally based on the magnet feed. Sorry, my brain wasn't getting around to it. About the material that's required to make the magnets, and it's some light rare earths and some of the heavy rare earths, and those are really the four most important. But you can see the prices of those things on US dollars per kilo. They vary quite a bit, and we know, depending on what's going on out of restrictions, supply restrictions around the world, that these numbers can actually jump around an awful lot too. Next one. So for me, and a mantra that I always use, mineralogy always matters across the minerals industry. My metallurgy people get that because they're the ones that actually have to extract the metals from the minerals. Geologists, sometimes we lose sight of that detail, and it's not just the in situ grade in the deposit that matters, or the in situ tons, it's how we're going to recover it. When I first started thinking about rare earths a long time ago, and even when they were first setting up Olympic Dam and do the pilot plant days back in the 80s, they were already looking at things like scandium and rare earth elements, because they knew that the rare earths were actually elevated Olympic Dam, but they were even looking at it back in the 80s. So when we're looking at these things and saying, really, what's the treatment path for rare earths, and there's more bespoke things coming on, and you as metallurgists, I'll just lump you all as metallurgists, hopefully you're designing more methods or methods to extract these materials out. But really what we know, that there's a pre-treatment and sorting, beneficiation, where you end up making a rare earth concentrate that's got about 30% rare earths. It fluctuates a little bit, but you have to go for whatever your ore grade is, or your kind of pre-enrichment is going into that plant, up to about that type of product. Then we go into get away from physical separation, really into the hydrometallurgy world, where you take that rare earth concentrate and then you make it into a total rare earth oxide product. And then the real value is in it is then when you separate all those rare earths, and that's very bespoke side for the refining, but really the solvent extraction side, highly intensive process, but that's what has to be done to recover these rare earths. Now, all the rare earth minerals that are around, and there's a lot of them, are not all created equal. And of course, we want the rare earths that have the most rare earth oxides in them, obviously. So things like bastnasites, a rare earth carbonate, monazite is a phosphate, xenotime is a phosphate, and just go down that list. And the important thing to know is that it's above that little tiny orange line. Those minerals, or those 4 minerals up there, are the ones that have a commercially viable process to extract those rare earths from. So we get all excited about all the other low concentration things around, but all those other minerals, excluding the ion absorption clays, which is a different story altogether, they have processing challenges and there's complicated mineralogy. So even deposits, they say they're elevated in rare earths, if they're loaded with these other minerals that there's no process to extract them, that becomes a problem, as you guys are fairly well aware of. Next slide, George. So we're going to come back to Olympic Dam, big, huge deposit. We have over 120 minerals that have been characterized in our ore body, and that's from the macro scale, and it continues to look more, we look at the nanoscale. That's from the macro scale down to the nano, and that characterization is just ongoing with time. And fortunately, about 15 of those minerals account for greater than 99.5% of the ores. Including in that is the sulfides, which we recover, which are in the boldface side, up on the upper left. The rare earths, which are highlighted in blue, are uranium minerals, are uraninite, coffinite, buraninite. Then there's a whole swag of gangue minerals too. And it's important for our plant. We'll just show a brief flow chart in it, because each of these mineral groups, but they're really mineral groups, have their own set of processing characteristics, particularly when you're in a place at Olympic Dam, that it goes from milling, grinding and flotation into a hydromet circuit. We make a concentrate and then gets partially leached, smelting and refining. So each of those minerals behave differently in different parts of that plant. So it's not complex, but I'll say it's complicated. Next one, George. So the Olympic Dam rare earth mineralogy, and we actually have a couple more in there. The ones that we know about are things like bastnasite, fluorensite, centrosite, monazite, xenotime, and it shows what their rare earth concentrations are. But our uranium minerals, of all things, also contain an appreciable amount of rare earths in them, but they're very relatively low concentration in the ore body. And then you have some of these accessory minerals that also have some rare earths that are really not even shown on there. But by far, our 2 dominant rare earth minerals are bastnasite and fluorensite. Now, the photomicrographs, SEM images, again, 100 micron scale in the upper and 50 micron on the lower, and the bright stuff is the bastnasite. And that bastnasite size, you think, well, those are reasonable sized things that should be relatively easy to separate. Yep, those are, but those are just nice pictures that show up the rare earth minerals well because they're big enough to show them. That's not what's representative of the ore body. Next one, George. So a grossly simplified ore processing flow sheet for Olympic Dam, where we do mineral processing, hydromet, pyromet, and electrometallurgy all at Olympic Dam. Underground mining, and we're just going to really think about the copper and uranium ore stream. Goes on to ROM up on the surface. We have 2 big mills and a smaller mill. Sulfide flotation. During sulfide flotation, where we're separating obviously the sulfides from the gangue, the overwhelming majority of the copper goes into the copper concentrate, and about 90% of our uranium goes into flotation tailings, and that's why we actually leach it to extract that. And it turns out that a fair amount of rare earths are also going out in that tailing stream also. The copper concentrate goes through a leaching process. There is a little bit of uranium in that. That leaching liquor goes back into tails leach. That copper concentrate goes into a flash smelter. We make an anode from that. That anode goes into electro refinery of where we're recovering our gold and silver from, and eventually into the slime side. Now back on the tailing side of it, the flotation tailings, which again is about 95% of the total mass of that rock that we're sending through the plant or delivering to the plant. the primary purpose of tailings leach is to extract uranium, but there's a little bit of copper in that too that we actually are able to leach out. That mixed liquor that contains uranium and copper and a lot of solids still goes into a CCD circuit to separate solids from liquids. Then into a copper and uranium SX plants to separate the copper and uranium in solution. Copper into SX, and then to make EW cathode into the refinery to make EW cathode, which is a lower quality material than what our ER is, which is the 5/9 pure product, and which is the bulk of our copper. The uranium, though, in that solution, after the copper side is taken out, actually goes through and it goes in. We make a ammonium diuranate, so true yellow cake. And that yellow cake then goes into a calciner at 800 degrees to make uranium ore concentrate that goes, that's what our product is that we shipped off. And that all gets put on ships and goes overseas. Out of CCDs is where all the waste streams actually end up going. And that all goes out to our tailing storage, which to right now we have roughly 240 million tons plus or minus a little bit. So everything's locked up there. So the beauty on this circuit is all the extra complications, but when we have a circuit like that and we have an ore body that has multi-metallic streams in them, and even though we're only recovering a few of them, if we monitor our plant quite well, we can actually understand where things might be enriched. Things like cobalt, let's say, or any other topical metal that actually happens to have a spike in the commodities trading for a while. We actually know where they're occurring in there, which once we know where they occur, gives us an idea about how we're going to actually potentially recover it or do the evaluation work to say, is it worth recovering it? Next slide. So the way we do it, a lot of words off of here. We've been fortunate Olympic Dam because the complicated circuit and the fully integrated circuit, we've had a long history of doing monthly composite samples out of critical nodes all across the plant. And then that includes the material that's going out to the tailings dam, where we assay for the full periodic, or damn near the full periodic table. We do an analysis on a size by size basis because that's all important. We also do detailed mineralogy, not only assaying, but mineralogy off of all those products. And we've been doing it at this scale since 2003. We're very fortunate because of that circuit that we do this type of work, because it has far other applications than just improving the process on a day-to-day basis. We also have, and the monthly composite program is really a backwards looking. It's what's gone through the plant, but what's more important is predicting what the future is going to look like. And that's all around the geomet side of the world. And from the geomet, we do samples all the time that represent what our future ore is going to be coming out of those stopes. And we do laboratory grinding, flotation, and leach test. We also do all those assays and sizing, or we do sizing and assay and full mineralogy on a size by size basis to understand what's going on. And that provides us a massive, powerful data set of element and deportment models for 65 elements across 60 odd minerals on a size by size basis. So we have a good idea on where everything is going and what might be possible recovery options. And that allows us to quickly assess things like rare earths, or believe me, in almost anything on the periodic table, we've had questions about, through at various points in time. So we're fortunate here, and this is where I'll blow our own trumpet, that Olympic Dam, our geomet program, and what we do here is not because we're BHP and we're a large organization and can afford to do it. It's what's required for us to manage our ore body, not only on a short-term basis, but to make decisions about this deposit for what its future will look like. And this deposit will still be mining it 100 years from now, as long as there's a really a market for copper, what it really gets down to, and any other kind of thing that might pop up in the future. Next slide. So we're just going to use an example of rare earths, and we look in the upper right-hand corner. So the typical, over the last 5 years, the total rare earth oxide feed into our plant is about 0.7%. 97% of that is light rare earth oxides. 3% is the heavy rare earth oxides. Neodymium makes up about 53% of the value of the total rare earth oxides. And neodymium, praseodymium, and terbium are 82% of the total rare earth oxide value. So it really is around a few rare earths. But let's see what happens in the processing plant. So in the processing plant, we're just going to take that 0.7% and say that's 100% feed and do kind of a very gross balance across here. And these rare earths in a sulfide flotation circuit really don't recover to concentrate. It's the sulfide concentrate they're not exposed to. They go out to tailings. And you can see the first thing that tailings in the tailings leach residue after hydromet, that 92% of the total rare earth oxides actually end up in our tailings solid. And there's 6% that's actually in the leach liquors. And you say, well, that's interesting. And we won't worry about that cons leach feed in. And this is important to understand that, yes, our current tailings leach circuit is extracting a little bit of rare earths. It's not rare earths from the rare earth minerals. It's the rare earths that are contained in the uranium minerals that we're actually dissolving. So we do have a little bit of in there, not a lot, but we know it's there and we know why it's there. And we have considered options to put a plant in to strip that material out. It's frankly not worth it to do that because we have a recycling load, and as soon as you drop that down, it goes down quite a bit. We'll drop down to the blue box in a minute, but on the right-hand side, the sulfide flotation concentrate, yep, 2% of rare earths go in that. When we do a concentrate leach in order to strip a little uranium out, but then we also take a little bit of copper, that we can see in the cons leach solids, the material that's going to be the feed into the smelter has 1.6% of our total rare earth stream. There's a little bit of rare earths in that leach liquor because we've stripped, we've dissolved the uranium minerals out. That goes back over to tails leach. So in the smelting side, we still, because we don't smelt 100% sulfides, we actually have a little bit of gangue minerals in our concentrate. And during that smelting process, the copper that's generated from that, or in the blister, that anode really contains no rare earth elements in it. But the electric furnace slag, which is one of the exit streams, besides sulfur going into our acid plant, but the iron and the silicates and all that are left there, the rare earths actually end up in that slag. And then ultimately you can see down in our balance that of the original rare earths that entered the plant, that 94% end up in the tailings, and there's about that 6% over there. Now, don't change on me yet, George. When we look at the endowment for the total rare earth oxide Olympic dam, it's quite high. Bastnäsite and fluorensite are the dominant ones. But we know by doing all these measurements on plant composites over years and years and years, over 2 decades plus, and doing very detailed mineralogy across the ore body, that the average rare earth grain size is less than 9 microns. Now, you process engineers get that, that's not a trivial thing to go after. And that's not a trivial thing to go after because given our range in gangue minerals that we have, all the way from silicates to hematite, with all the different physical properties of those things, the physical properties of the rare earth minerals sit in amongst the physical properties of all of our gangue minerals. So that's a challenge in itself. You say, well, then gravity doesn't work too well. Magnetic separation doesn't work. Electrostatic separation doesn't work. There's a lot of these things just don't work because that group of rare earth minerals actually have the same, they span the physical property range of what all of our gangue minerals do too. So there's nothing unique about them. Now, next slide, George. I can see you taking notes. We'll give the prof there a little dig. We also, the things that are interesting, so even when we don't have access to full detailed mineralogy, we're very privileged to do that. What I learned from a metallurgist 30 odd years ago is that sizing assays on a size by size basis, if you know what's going on with the mineralogy, it actually reveals quite a lot. And in our deposit, it certainly does. So what we can look at, what we're looking at on the left-hand side, log scale, and nominally just a screen size, and those just represent a bunch of future ore characteristic samples. And just looking at what the mass proportion, the recovery is for each of the size fractions. And we go down, and there's not a whole lot of difference, 75 microns, 53, 29, we're down into the cyclo size fractions. Once we're down about 14, below 14 microns, all of a sudden, the mass proportion of those rare earth minerals starts to skyrocket in those remaining size fractions. And you can say, well, either I've ground a very coarse mineral down, or most of those rare earth minerals are actually naturally down in that size fraction range. So it's a combination of both, but we know by doing more in situ measurements on samples that haven't been subjected to what metallurgists do. And I say what nature put together might have taken 1 billion years to form an ore deposit. Metallurgists usually unravel that within weeks. It's usually unravel that or reverse engineer what nature did. You're trying to take that ore body back apart. But we know that the average rare earth mineral size at Olympic Dam is 9 microns. So difficult. Now we can also look at saying, well, are we actually those different rare earth minerals that have a different rare earth concentration pattern? Are we actually somehow magically putting a specific rare earth mineral down into a fine fraction and keeping the coarse, or maybe another one at a coarse fraction? And what this is a chondrite normalized example of one of those samples that I showed on the left-hand side. And what that chondrite pattern does is just normalize it, so we don't see all the spikes that we usually see when we're going odd, even on the periodic table. And that just allows us to make a little bit smoother transition. But what we see is there's no change in that rare earth pattern as I'm going across the different size fractions. That the absolute concentration of the rare earths in it is changing, as we know that. But the mixture of the rare earths going into those size fractions is no different across here, because some of those rare earth minerals are quite enriched in heavies and some are enriched in light, and they have different patterns in there. So we'd be able to pick that up quite easily. So this kind of confirms, even without doing detailed mineralogy, that we know these things are fine, and that's actually confirmed by all the test work that we've done. Now we'll go on to the next one. So the Olympic Dam, the rare earth challenge, and it doesn't mean we're ever stopping, and the journey that most places in the world start, really at this, roughly this 3%. It's dropping down a little bit, 3% to 10% total rare earth oxides in their ores going in. They then get concentrated up to roughly that 30%. These days it could be 20, maybe a little bit higher than that, maybe a little bit less. And then that rare earth concentrate then goes into a solvent extraction process in order to get those out and extract them all. Now, a couple things that I have on here. So where are we on that curve? We come way down at the bottom. Olympic Dam's feed is 0.7%. Our ores have similarity to Bionobo ores in that they're both iron rich. Grinding, milling, and total rare earth oxide flotation has not been successful at improving the total rare earth oxide grades for Olympic Dam material, and neither has gravity and magnetic separation. We could throw that in there. High intensity. Average grain size is 9 microns. We have R&D projects in place to develop whether it's technically viable, but not necessarily economic. The first thing we got to do, and particularly on the research side, is what's technically possible. Economics is something applied after you come out with a viable processing stream. And we think for a minute, we look at what can we learn from Bionobo, that their rare earth production is a co-byproduct of iron ore, of iron ore production. Their rare earth mineralogy is actually modified by reductive roasting in the production of the slags, and so they then take their slag from their iron ore process, do a reductive roast, control the cooling rate, then allows monazite to grow in size big enough that becomes amenable to grinding, milling, and flotation to produce their rare earth concentrate. The recovery of their rare earths is less than 30%, the best I can glean out of the literature. And because this is such an energy intensive process, you think, to deal with all those extra slags, it's an economic if that process is done outside of China because it's so energy intensive. But it still provides us an idea to say, well, let's look at what we have going on Olympic Dam. We actually have a smelter, and we do have at the end of the process, our electric furnace is a reductive roast. We actually do grow monazite inside of that, but it's very, very small. So by looking at how they're producing it elsewhere, we can say, well, how will that apply back at our site and stuff? So we try to learn everything as much as possible from other producers. Next slide, George. So once we've actually come up with a technically feasible process, the forward decisions are really based around trade-off studies, and particularly in a deposit where we're already producing copper, already have commodities there. Could we produce something else? Sure. You look at what the revenue gain is versus the cost increase, the impact on your primary metal streams, what the market impact is, particularly if a big producer comes online, what the operating risk, and what's more important is the ESG risk that we all have to be completely aware of today. I think I'm coming down, ripping to the end here, George. So these are a couple air photos, and the air photo of the current operations at Olympic Dam. And the scale on there, first of all, that blue outline is roughly the resource outline. So our kind of 11 billion tons of ore sit within that outline at greater than 350 meters beneath the surface. And the diagonal for scale is about 6.5 kilometers along that ore body. And that ore body has continuous mineralization along that 6.5 kilometers. It's a thing of beauty. The two yellow dots, the first yellow dot on the very, very lower edge of that blue is where the discovery hole was. And then the second yellow dot up a little bit north of that is actually where the what was called RD10, which actually showed the size of the deposit. Now that's where we sit today. Back when that deposit was first drilled, that air photo was just prior to drilling out Olympic Dam. And that's what it looked like out there. So as an industry, we do go through and we transform the areas that we work in. We just don't walk into an area that's fully developed. And you think about all the professions that are actually required to go from something like sand dunes, and we are actually in sand dune field out there, to producing metal, what we are doing today. Next slide, George. And not only, this is an air photo that shows Olympic Dam, the operations itself. And in the middle of the photo is where the airport is and Olympic Dam Village and our light industrial complex. And then there's a town further to the south of that, which is called Roxby Downs. And that distance between Roxby Downs and the mine site is about 13 kilometers. Now, WMC built the town and they built the airport, not the scale that it is now. And they built the mine and the underground all at that time. And then the roads all the way up from Pimba. So the town was built in 1986. It has a shopping district. So where we out in the middle of the bush, shopping district, schools, police station, motel, multiple restaurants, hospital, sporting facilities, etc. Population peaked at about 4,000 people. The nearest rail siding is 92 kilometers away at Pimba, which is along the Stewart Highway. The water from the mine site and the town is sourced from the edge of the Great Artesian Basin. We have bore fields that's 110 and 200 kilometers away from Olympic Dam. And it goes through that water's hypersaline material, and it goes through a reverse osmosis plant at Olympic Dam to produce human consumable water and then other water that can be used in the operations. The airport at Olympic Dam has accommodation there, and mainly for FIFO workers. And we also have accommodation for FIFO workers at Roxby Downs. Some of the workforce is residential. When I worked up there, I lived up there for 14 years. And at that time, everybody that worked there actually lived in a Roxby Downs in a more modern sense. We're shifted now towards more FIFO. The underground mine itself has more than 700 kilometers of underground workings, and we're adding to that number every year. We have 61 surface vent raises, which is exhaust and intake to ventilate that mine because we're far enough underground, but we also have to ventilate radon gas out. And so we still think about that. So you say we've gone from a mine site and what professions might be needed by that. We also have a town and the building of that town and the running of that town. Now that's an open town, but think about all the facilities that are required to sustain this operation. Final one, George, I think. So when we're thinking about our careers, I have never, ever regretted a single day that I've worked at Olympic Dam over the last 33 years. And I am getting very gray hair, and you'll say getting a hell of a lot closer to retirement. But it is one of the most exciting places to work, and opportunities that the minerals industry provides is vast. And we think about what's the work for everybody. The industry needs every profession and trade that's around that you can imagine, because unfortunately, we don't have mines that sit up near Cairns or Brisbane, or some close to Brisbane, but we don't have all nice kind of coastal locations, and most mines around the world are becoming more and more remote areas. So we need everybody, and so that means the opportunities are there. The industry is a lot more flexible on how they take on people, but still it's a great place to be. And there are opportunities for every single profession. And so with that one, George, I would like to just go end on the last one. Thanks for your attention. We do not go down this path alone. I have built on the shoulders of my predecessors at Olympic Dam, people that designed those flow sheets, people that discovered that deposit, all these people that actually helped develop that place. But we also have a lot of collaborations with Times, with all these different groups that are listed here, and we're fortunate enough to get ARC funding, have got some joint funding with the ARC. The South Australian government's a big supporter of us, obviously, and the different universities, ANSTO and CSIRO too. So I'm open to any questions, George, and thank you.
Thank you very much, Kathy, for a fantastic talk.